Recording. Oh, okay, here we are. So, well, good afternoon and good evening, everyone. I am Eduardo Serpa from Chile. I am the chair of today's third seminar. Okay, so and it's a huge privilege for me to introduce Manuel Del Pino from the University of Bath in the UK. Also, brief lines about Manuel. So he started his studies in mathematics at University of Chile. Then he got his PhD from University of Minnesota in the US in '92. After he spent 1 year at the Institute for Advanced Studies in Princeton and got a Dixon Instructor position at the University of Chicago. Back in Chile in 1995, he developed his career at the University of Chile, and since 2018, he is full professor at the University of Bath. Among other recognitions, I would like to mention that he was invited speaker at ICM 2010 in India in the section PDE. He's a fellow of the Chilean Academy of Science, and he got the National Prize of Science in Chile in 2013. And he got in 2018 the Royal Society Research Professorship in the UK. He has written many fundamental works in PDEs, published in the very best mathematical journals, with a huge impact in the community, as we can see with his more than 8,000 citations in Mathsinet, for instance. Okay. For today, the title is Vortex Dynamics in the Gross-Pitaevskii equations. Okay. And so, Manuel, we're very pleased to have you here. So you can go ahead.
Okay. Well, thank you very much, Eduardo, for the very, very nice introduction. And thank you also to Juan for the invitation. So it's the second time I have the opportunity to speak in this seminar. So, well, it's an honor for me. By the way, how much time do I have?
Yeah, 45 minutes.
45, okay. Okay. Well, the topic of my talk today is what you can see in the first slide. So I will speak about some recent results we have on vortex dynamics for the Gross-Pitaevskii equation. I will introduce to you what the equation is, of course, and rather than its direct applications, which are many, by the way, I will speak about the link it has with the fluid dynamics, with more standard fluid dynamics, okay, with incompressible Euler in particular. Okay. Oops, no, this happens to me sometimes. Okay. Okay, so let me start with to remind you, the standard dynamic equation for an incompressible fluid with no viscosity. Okay, this is very ideal conditions. So this is a transport equation, yeah, transport type equation, and P is a scalar function, so the pressure, and V what represents is the velocity field for the equation. This expression or this equation makes sense in 2, 3 dimensions and even higher dimensions, okay, already probably non-physical. I will restrict myself in this talk to the 2-dimensional case, okay? Now, if we take curl to the equation, okay, to both sides, then I get 0 on the right, of course, and the nice thing is that the curl of a gradient is automatically 0. Okay, and not only that, the curl of a vector field with 2 components, okay, and of 2 variables, can be interpreted with a scalar that goes in the third direction. So the curl, we just think for this purpose that it is a scalar, okay? So, and that scalar satisfies a very cute equation, this one. So it is the curl of the velocity field is called the vorticity, with good reasons, okay? Because it's precisely a measure of how much the fluid is rotating around a given point at a given time, okay? And it is, as you can see, directly transported by the vector field v, the velocity. Now, if we have the solution for vorticity, we can actually recover the velocity field simply by a direct formula, okay? If maybe I need to impose some condition at infinity, like the solution going to 0 or having some integrability, something like that. But it can be typically recovered through this formula, which is called the Biot-Savart law. Maybe you can see what this guy is. This guy is the gradient perp of the fundamental solution. So this is essentially the gradient perpendicular of the fundamental solution convoluted with omega, with the vorticity, which is nothing but the Newtonian potential of the, or the inverse Laplacian of the vorticity. Okay, so you take the gradient of the Newtonian potential of the inverse Laplacian of the vorticity, and you take the perpendicular of that, and with that you recover the velocity. So it's a relatively simple law that also has its suitable versions in bounded domains when you impose suitable boundary conditions. But I will restrict myself to consider the problem in entire space. Now, let me tell you about a very classical situation, okay? Which are solutions of the equation with highly concentrated vorticities. What do I mean by highly concentrated? Essentially, what I mean is that the vorticity is supported at a finite number of points. Of course, you know, a nice function cannot be supported just at a finite number of points, nice smooth functions, okay? But I can idealize the situation in which the vorticity can be written as a linear combination of Dirac deltas. This is what I mean by this symbol here, and centered at certain points that I will call generically with the letter A, Aj of t. So this is a Dirac mass at Aj. If you wish, this guy is a function, sort of function, with integral 1 and with support exactly at the point Aj. And okay, and the mass of the whole thing is of this object here is just a scalar gamma j. How do I recover the vorticity, the velocity, sorry? Using a vorticity of that form, well, I can recover it through this formula, the Biot-Savart law, and where k, remind you, is just this thing here. So this is not so random. It's not that if you fix, you know, arbitrary functions of time, points in space, in two-dimensional space, Aj of t, this guy is going to be a solution. No, we need certain connections between mutual dependencies between the Aj of t. And that comes as simply as a system of ODEs that I will derive for you next. This is anyway very standard. It's nothing so special. But let me do the following. Let me substitute this expression into the equation. If I do that, what do I get? Well, first, the velocity v, I remind you, is this sum here. Yeah. So I will call each of the elements in this summation, I will call it vk, okay? So if I stay at this around a single j, okay, then I can write v equals vj plus a remainder, where vj is this guy, right? Vj is this guy by definition. And this notation, v different from j, means simply the sum of all the vj's with j different, sorry, of all the vk's, I should say, with k different from j, okay? If you wish, it is like the regular part of the velocity, because this function here is singular. Now, formally, the Dirac delta, imagine for a second that Dirac delta was a function, or that it is simply the limit of a spike of a radially symmetric spike, okay? With high amplitude, with large, very high amplitude, so that the mass is equal to 1 and very small support. Okay, so you can imagine that the Dirac delta is a radially symmetric function. Well, in a sense it is, because it is invariant under rotations. Yeah, the Dirac mass is invariant under rotations around aj if you consider it as a function of the translated variable x minus aj. So this guy is radially symmetric, and if it is approximated by radial functions, and the gradient of the Dirac mass is therefore a function, a scalar function of x multiplied by x minus aj, because it is something that points in the radial direction, right? Say the gradient of a radial function points in the unit r direction. On the other hand, the k is this guy, which is a scalar multiplied by x minus aj paired. So when you do the dot product, this is immediately zero. So the contribution of this term, when you make the dot product with the gradient of delta aj, this is immediately zero. Therefore, this is only formal, what I'm saying. Now, since the self term vanishes, then the whole v dot gradient delta aj, I mean, it's not too risky to be identified by simply the v different from j dot the gradient of delta aj, okay? This function which is regular at aj. And the support of this whole object is the point aj itself. Now, this field v different from j is smooth near aj, and we have therefore that this product can be written as simply the smooth function evaluated at aj. This is a scalar thing, right? A vector actually, dot gradient delta aj, and therefore this product v dot gradient of delta aj is simply this sum of k different from j of this guy evaluated at aj minus ak, dot product with the gradient of the delta aj. Now, let me simply use chain rule to write a derivative in time of the Dirac delta of aj as simply as the gradient of delta aj multiplied by minus aj dot. So I am simply using formally again, if you wish, chain rule, okay? Chain rule for a composition of a distribution with a function. Now, therefore, for the definition that I had of the vorticity, omega t is therefore this sum here. When I combine then the expression that I already got for v dot gradient omega, then I get, since this guy is v here, yeah, this guy here is the v, then I get simply v dot gradient delta ij. And therefore, when I substitute the entire operator, the entire transport operator for the vorticity, I directly get this expression here. So in order for this guy to be zero, what is necessary and sufficient, identically zero, these distributions are certainly very singular, not zero. And the guys here, the quantity here between brackets, it should be zero, right? In order for the equation, the Euler equation, be satisfied. And that amounts to simply a set differential relations for the points aj. So aj dot equals this sum here. And in this vortex dynamics law, okay, this is indeed very old, okay, it traces back from the very origins of the analysis of fluids through these equations. And this is called the Kirchhoff-Rosse point vortex law sometimes, although the origins are in all these, needless to say, highly famous people, right? Helmholtz and Kirchhoff in particular started the analysis of fluid dynamics with this type of equations. Okay, so this what you have here is a Hamiltonian system. Okay, it's not just a simple ODE thing. Okay, it's a nice equation in the sense that it has an energy conserved. Okay, now, therefore, in order for an expression like this be a quote solution, then you need that the points aj satisfy that differential equation, that differential system. But here is a classical question. Say, this is true for this point vortices law, but can I find true solutions imitating these dynamics? The answer is not completely obvious. Are there, say, what happens if I perturb the delta to convert them into smooth functions, okay? Then the question is, do I really have solutions that look similar to this configuration with the AJs evolving through the Kirchhoff-Roche system? And the answer is yes. There are different qualities for this answer, and we got one a few years ago. Let me tell you one way in which I approximate the Dirac deltas, okay? I will take this function, which is convenient for me, okay? No, it's not the only choice at all. I could use other things. Then I consider this function that I call capital W, and this is a radially symmetric function. Let me observe that the velocity field associated to a radial function, yeah? Remember, that's the gradient perp of the convolution of a radial function with the fundamental solution. That's the radial function itself. Therefore, the v dot gradient, this guy, is automatically zero, yeah? So this is tangential and this is radial. And therefore, v dot gradient omega is zero. Therefore, radial vorticities are a stationary Euler solution. So a radial function is a stationary solution to the Euler for incompressible Euler. Therefore, I will take this specific function, which is convenient for me, decays sufficiently fast to make the mass finite in particular. The mass of this guy, when I normalize it with this 1 over pi here, is exactly 1. This is convenient because what I want is to use it to approximate Dirac deltas. How do I approximate Dirac deltas? I scale this function W naught like this, like 1 over epsilon squared multiplied by omega naught and multiplied by scalar gamma, of my choice. If I let epsilon go to 0, what I get is a spike, highly concentrated near the point A, okay? So, and with fast decay, and therefore in the limit, distributional, weak limit, I will get constant gamma multiplied by the Dirac delta A. So I can formally recover the Kirchhoff-Roche dynamics of the vortices. If I consider several of them, okay, like this, I consider a vorticity as a linear combination of gamma j's multiplied by these scale guys, and I let epsilon go to 0, and then I get the sum of Dirac deltas at the points aj, and therefore what I will have is the well, here I should say aj dot, okay? And this is the Kirchhoff-Roche law that I stated before. Okay, so this is what I try to represent, or this is what people intended to represent like this. So if you put several cyclones, okay, between United States and Europe, okay, I don't think anything like this has ever happened, but it's but just to fix ideas, then you see what we have. We have this highly concentrated vorticity, okay, for the atmosphere, of course. However, this is not singular. At the center, what you see is the eye of the hurricane in which you have velocity 0. So you have a smooth distribution, very spiky for vorticity, okay? But at the center, and this guy is perfectly smooth. And there's no velocity here. Say simply no. At the center of a hurricane, nothing moves. Okay. Now, concerning what I was mentioning before, say I have a sort of approximate distributional solution if I plug in something like this with centers aj satisfying the Kirchhoff-Roche system. But what is not obvious is that you have a true solution that looks like that. And we prove there is an exact solution, a true solution of the system. This is joined with Juan Davila, Monica Musso, and Junchen Wei. Okay, we published this a few years ago. And In fact, I think I spoke about this in the previous seminar, the previous time I was here in the seminar. And there exists solution to the Euler system of this form. So this approximation plus a remainder which is smooth. And look at how the remainder is made. This guy has 1 over epsilon squared in front, so this is huge near the origin, okay? The origin AJ is like 1 over epsilon squared. It's extremely high, and then it becomes small. In fact, very far away, it becomes very small. This is 1 over r to power 4. So, you know, very eventually, very far away, this guy even picks up, okay, compared with this. But you can say that it has quite a nice decay. This guy is like epsilon squared. So is epsilon to power 4 times smaller than this thing, if you are at the point AJ, or very close to the point AJ. And when you go far away, you get epsilon squared over 1 over r squared. So if you want that this guy wins, you have that this guy wins with respect to the main guy, you have to go to distance which is already beyond the order 1 over epsilon. So it's very, very far, okay? So most of the time, this guy is small. It's very small compared with the main answers. In particular, let me observe that if I take the distributional limit as epsilon goes to 0, I get the sum of the gamma j's Dirac delta of AJ, and in addition, the kinetic energy, the density of kinetic energy, which is this guy. When you normalize it with 1 over log epsilon, then you get again a linear combination of Dirac deltas as indicated here. I insist in this because of one thing. We are not the first ones in working on this. There was a very nice work, very interesting work by Marchioro and Pulvirenti in the early 80s. And Marchioro and Pulvirenti, what they found was that if you start with compactly supported, you know, radially symmetric bumps or something like that as initial conditions, and you normalize them in this way, then eventually you will get this distributional situation when you let epsilon go to 0. And what they do is really use the definition of distributional solution, of weak solution, and take limit inside it after having certain control on the support. Essentially, the main element in their proof is a control of how much the support could grow, because the support of the solution is something you can hardly control in a very precise way, okay? However, with the type of method that we use, we find an exact asymptotic expansion near the centers, and this is the big difference with their approach. In particular, with their approach, they are not able to capture this configuration, which is just distributional conversions. Okay, so our method, if you wish, is harder in a way, but the answer that we get is much more precise. Now, let me go into the Gross-Pitaevskii equation. The Gross-Pitaevskii equation is this dispersive equation here, and I will consider it with the right conditions at infinity, which is the absolute value of u going to 1. U is complex value, no? So this absolute value is a complex absolute value. So as x goes to infinity, this goes to 1. And I will tell you in a moment why is that is natural, so later on. So this is a complex thing, and it turns out that you can write this as an infinite dimensional dynamical system, which is Hamiltonian by itself. In fact, it is a Hamiltonian evolution for a specific energy, which is this one, okay? This is like the standard Euler-Lagrange, or this term is like the Euler-Lagrange equation, okay, associated to this energy, yeah? So this is like IUT equal gradient perp of this energy. This is not gradient perp, is IUT equal gradient of this, okay? And that's Hamiltonian. So the applications to physics, or to serious physics of this system are well documented in the literature. Say it's sometimes called Ginzburg-Landau theory as well, and it arises in the modeling of superfluids and superconductors. Essentially, this is phenomena that happens at extremely low temperatures. So you get a fluid that has doesn't have any viscosity in reality. No, it's not only incompressible but not viscous, but in a perfect but realistic way. If you consider objects like liquid hydrogen or objects like that, those are superfluids. And superconductors. For superconductors, it's a similar thing, okay? And that's the Ginzburg-Landau theory. If you consider something that is called the hydrodynamic formulation, you can see a deep analogy with the standard incompressible Euler system. I will discuss this in a moment. And that hydrodynamic formulation corresponds to writing the U, in polar form in this way. This is a complex number, I remind you, and rho and phi are scalar functions. Now, if you consider the gradient of this scalar function, phi, I will just give a name to it. Huh? I will call it velocity. Okay. You may wonder what has this to do with the velocity in fluids. I will tell you in a moment. And even this number -2 that I involve in the expression is because it is convenient, nothing else. Now, the Gross-Pitaevskii momentum is this vector. Okay, what is this vector? You take U, the complex guy, multiply by I, and multiply that complex scalar by the conjugate of the gradient of U. Okay, gradient of U is a vector with complex components. Okay, you take the conjugate of it and multiply the whole thing by IU. Now, if you use this convention with the magnitude and phase, okay, then the gradient of U can be written in this way, and therefore, if you do IU times gradient conjugate of U, you get exactly this expression here, yeah, which is quite reasonable, right? If you take real part, this R means real part. Huh? If you take real part, the real part only involves this guy. So you get rho square gradient phi and I square. So when you take the real part, you get essentially the velocity, except that it comes multiplied by this rho squared. Okay. If rho squared was constant or it was equal to 1, then this guy would be directly like the velocity that I defined before. So, but it's not velocity, it's momentum, okay? So you're multiplying it by mass. And this is called momentum or current for the solution. Okay, what is vorticity now? Or what should play the role of vorticity? The role of vorticity is again something like the kernel of the velocity, but not quite. It's the kernel of the momentum, okay? If you compute the kernel of the momentum for the function that I expressed before, in terms of the polar U given by rho times e to the a5, then you get this easy expression. Okay, it's rho times the determinant of the 2 by 2 matrix, which is this with these two things as columns. Okay. Now, what is the connection between incompressible Euler and Gross-Pitaevskii? I will tell you next. For incompressible Euler, I have this equation, right? So it's the transport operator, or this nonlinear transport, okay, equal to negative gradient of the pressure and the zero divergence condition, the incompressibility. So the known is the velocity field, which is this V1, V2, and vorticity can be identified with this scalar. This is the only component it has, okay? dx1 of V2 minus dx2 of V1. Now let me consider GP. So if I consider GP and I write U as before, rho times e to the a5 with these conventions, then you can see the absolute value of U squared is rho squared, of course, and the Laplacian of U, if you do the computation of the Laplacian of this product, this with this, then I arrive to this this situation here, this expression here. Okay, so I will separate the real and imaginary parts. If I separate the real and imaginary parts, and substitute inside this equation, then I get this equation where that involves the magnitude, or rho squared. So this is 0. And I get, in addition, this conservation law, and I get in addition this equation down here, which is phi t plus gradient phi squared plus this guy that involves rho again, equals to this object that is again a function of rho. And since v is the gradient of phi, I will have that v squared can be written in this way, right? Gradient phi squared is 1/4 of the velocity squared. Now, if I take gradients in the equation that I just showed you, this one, yeah, then I obtain this equation for v, yeah, for the gradient of phi. I get directly the gradient of phi, so vt plus this 1/2 gradient v squared plus these two guys here that both of them observe gradients. Now, away from the vortices, I will have that the curl of v is 0. Why? Because v is, vortices means zeros of v, of u, okay? What happens is that the function phi is regular away from the zeros of u, okay? And that's easy to see. And v is a gradient, so curl of a gradient is 0 automatically. And I have this identity, which is an identity of vector fields. Therefore, this guy is 0. And therefore, what I have is this. You may remember this guy that appears in Euler. V dot gradient v is nothing but the gradient of half of v squared. If I use that, then I obtain this very nice equation, which reminds us very much of Euler, right? So it is a version of Euler in a way, because if you call p super epsilon this guy here, this thing here, then the equation can be written as same as the Euler operator plus gradient of the pressure. But this is not fully Euler, okay? It's not incompressible Euler. Yeah, if to have incompressible Euler, I would need in addition this thing down here, divergence of v equal to 0, and I don't have that. However, when I get epsilon go to 0, in a certain sense, I recover the incompressibility. The continuity equation is what I showed you before, this one. The GP energy, the Gross-Pitaevskii energy, is this guy. And since this evolution is Hamiltonian, the GP energy in the trajectory, okay, of the solution, along the solution in time, is constant, okay? So it's conserved along time. You easily achieve that derivative in time of this guy is 0, just using the equation, okay? And so this quantity is conserved. You can write it in this form, of course, sum of positive things plus this guy, which is also positive. And then you can perhaps believe me, okay? The typical initial conditions that you take for this guy involving vortices are of order log of epsilon. And then, in particular, the integral of this guy is going to be less than epsilon squared multiplied by log epsilon then. And if you take square root, what you get is that 1 minus rho epsilon squared, L2 norm in space, is bounded by epsilon log epsilon to 1/2, and this goes to 0 as epsilon goes to 0. Then observe what we got. We got that as epsilon goes to 0, rho epsilon necessarily goes to 1. It does it in L2 sense. So it does it in, think that it does it even beyond L2, okay, or in other nice norms. And observe that the continuity equation here, up here, if I use rho epsilon squared goes to 1 as epsilon goes to 0, yeah, then what I get in the limit, assuming that there is a limit in a certain sense for v epsilon, then I get divergence of v equal to 0, because divergence of 1 times v is 0, and this is 1 sub t equals 0. So assuming that I can exchange limits with derivatives and everything, then I get finally the equation of the Euler equation, assuming that the pressure P epsilon also goes to someone, approaches something. Then I get the incompressible Euler. So what I proved, this is not quite a proof, okay? But what I got is that GP goes to Euler, incompressible Euler, as epsilon goes to 0. Okay, this is what I wanted to tell you. However, there are some important differences present. And one important differences are the circulations in the following sense. Vorticity can be taken having arbitrary so-called circulations. These are the gamma j's. Imagine the point vortex tree, for instance, and consider this scalar gamma j, and consider simply a curve C that goes around the point AJ, okay, near the point AJ, but goes around it, okay? If you compute the integral of V dot dl, say integral on the closed curve, the integral of this vector field on the curve, then this is like the circulation, right, of the velocity field around the curve, and but V is a gradient. So what you have here is that the work integral of a gradient of a function, and since the using that and using the fact that the kernel of a gradient is 0, then you end up having that the function phi, the phase, has to have the same values when you consider two endpoints, say one point of the curve approaching it from the left and from the right. If I do this integration on the curve along with those two endpoints, what I get is that the difference has to be a multiple of 2 pi. Okay, it has to be because it's supposed to be regular. Yeah, the e to the I phi is supposed to be regular. So if I use that argument, then I get that the circulation for the velocity has to be a multiple of 2 pi. Okay. Yeah, and this is a special thing for Euler, and instead for Gross-Pitaevskii, instead for Euler, in reality, since the V doesn't need to be a gradient, in fact, I can have that these numbers could be just anything. Okay, so this is the reason why I insist that these gamma j's are arbitrary, while in Euler they have to be integers, not exactly integers multiplied by pi. Okay. Now let me consider the steady state problem. Is this one? Okay, and this guy has solutions that can be written, the solutions of the degree k, okay? It's that have the form a radial function multiplied by e to the I k theta. So they have winding number k, and where these guys are 0 at 0, so these solutions have exactly 1 0, and that 0 has degree k, okay? So they have this form where this coefficient goes to 1 at infinity. Now, these solutions have been very much studied already, and in fact, for k equal to 1, they were established to be in a certain suitable sense local minima in the sense of the Georgia, I should say. And it appears here the name of Mironescu, of Shinikov and Segal, and ourselves, say, myself with Felmer and Kowalczyk, we established certain coercivity estimate for the uniform stability of the vortices of degree 1 and -1. Instead, for k bigger than 2, they are unstable in this sense. They are saddle points. Okay, so it's not clear what is the behavior if they split, for instance, or because the energy is preserved. Okay, but there could be funny things happening. So there is no stability in the vorticity sense either, in the vortex equation, the vorticities either. So if I denote the degrees of 1 and -1, the vortices of degree 1 and -1 in these ways, one is the function W, I will simply denote it like W, and W-1 is the conjugate. So it's you change just I theta by minus I theta. Then they are, if I scale them this way, then they are solutions of GP in this form, of steady states of GP. Okay, now if let me compute the vorticity of this object. If you do the very easy computation of the vorticity, you will quickly realize that you get this expression here, it is equal to this expression here, And this is a function that the W goes to 1, but W prime decays like 1 over R cubed, okay? And what you get is that then this guy is integrable, and if you compute exactly this number, you can compute it explicitly. This is pi, okay? So it's okay. So this is a fixed thing, pi. Therefore, J of U epsilon approaches pi times delta naught because this is concentrating. It's again a similar behavior as that of the highly vorticities in Euler. Now, how do I consider things that are analogous to the Gross-Pitaevskii vortice for the Euler vortices, but now for Gross-Pitaevskii? I will tell you how. What I will consider is an ansatz of this form, okay? This is a product, not a sum. A product of vortices of degree 1 with vortices of degree -1, okay? So this is the type of solution that I would like to have. Solution is a way of saying, because you may not have an exact solution like this. In fact, typically, I mean, very rarely or never, except for J equal for one of these things and this a constant, you will not have this solution. On the other hand, if you compute the vorticity, the total vorticity of this guy, you see that the main contributions are around the points AJ, and then what you get is that the vorticity approaches sum of Dirac deltas times corresponding degrees and times this number pi. And the centers turn out to formally follow the Kirchhoff-Rosse dynamics again. Yeah. So here is just a picture for the vortice of a superfluid. Okay. Then what we do is, what I try is to get a solution that has this form. This guy plus a small error. And it turns out that in the limit, if I substitute this in the equation, I will end up having something like the Kirchhoff-Rosse equation again. So this is what I mentioned to you before. You have the vorticity approaches this linear combination of things. And in the GP normalization velocity, then I get the Kirchhoff-Rosse system. Okay, and I will tell you now what we want to get. What we try to get is this thing. It's a solution that has this form plus a remainder, okay? So same thing we did in Euler. Now we want to do it in Gross-Pitaevskii. And this has quite a bit of history in reality. So Neu in 1990 proved that if the vortex core is smaller than the intervortex distance, okay, then the dynamics of n vortices of degree 1 and -1 is well approximated by the Kirchhoff-Rosse system. He makes a formal proof of that, okay? So, which is not surprising, but here the decays are only 1 or -1. Rigorous results in the sense of measure theory, of geometric measure theory, have been obtained by several authors, all of them, okay? But in summary, what they are able to get is that the vorticity approaches as we expect for a true solution as epsilon goes to 0. If you consider this very concentrated, then you get solutions that look like that have this property, but with no fine asymptotics along the course, namely the zeros of the thing. And this is our result with Rowan Junman, our student with Monica Musso. And it's not published yet, but you can find it in arXiv. What we found is a solution that looks exactly like this, where the points AJ correspond to a given solution of the Helmholtz-Kirchhoff system, or sorry, the Kirchhoff-Rosse, I was calling it. And the U epsilon looks like this product plus a remainder. What does the remainder? The remainder is of size epsilon square, essentially, or epsilon square at most modified by a log. And so it's small compared with this guy, which is capital O of 1 everywhere. On the other hand, let me add that this phi epsilon, unlike this guy has infinite energy, okay? However, this guy does have finite energy. This is the difference with the usual thing and comes from the computation. And we find something else in reality. We find that the phase actually comes modified by by a solution to a wave equation, yeah, that looks like this, yeah, and where the right-hand side f behaves like this for x very large. In other words, there is a regime which is near the course and another very far, which is then the true system is the Kirchhoff rows modified by a gradient term, okay? That changes the nature of the system completely because this is Hamiltonian. This system is Hamiltonian. If you add a gradient to it, the Hamiltonian is lost, okay? And that creates new phenomena, definitely. Let me finish or to conclude more or less by telling you some related things. One is the question that is natural here, right? What happens? Can you find solutions that respect this type of behavior as time goes to infinity? We have done this in incompressible Euler. And let me mention that we have a result for vortex pairs as time goes to infinity, joined with Davila Musso and Srish Parmeshwar, who was our postdoc. And it goes like this. You have two vortex pairs, okay? Vortex pairs are standard solutions, okay? And this travels with constant velocity to the right. And this one to the left, what is, of course, the sum of two solutions is not a solution. However, it turns out that you can find a true solution imitating or going along these ones. If you find suitable initial conditions, this is not for free. It's not obvious that these configurations are stable. Even orbitally stable is not clear. So this is what we found. This is recently published actually already. With this paper is in GEMS, appeared this year, and this is more or less the form of the solution. So this is the two vortex pairs together. And anyway, I will not tell you about the proof. The proof consists anyway, just to say just a single word, okay? The proof consists of finding a good approximation of the solution. Needless to say, we linearize around that in fact, we need approximations that are of high order in epsilon. Say, in fact, in suitable norms of size epsilon to power m for any m. This is what we end up needing, yeah? Yeah, and once we have this, we manage to create a nice linear theory, both for the elliptic Ginzburg-Landau and for the full problem, yeah, that uses somehow conservation of energy in order to solve the linear problem and use just a fixed point argument at the end. In order, it is very important to do the gluing between the outer regime, in which the leading behavior is a wave equation with this local behavior, which is nothing but the usual. This is called the radiation. This side, okay, and near the course you have an elliptic regime driven by Ginzburg-Landau. Okay, yeah, I think I don't have. Really time for more. We are trying to do this in 3D. This is called the vortex filament conjecture, in which the connection is with this flow, with the binormal flow of curves. We have good advance already in GP. In Euler, this is an open question, an open conjecture for more than a century. Okay, and except for you have very special solutions like vortex rings and helices and nothing else. And in fact, some time ago, we found a special case, or we proved this in the special case of a helix. And this is joint work with Remy Rodiak, who was a postdoc in Católica, by the way, quite a few years ago, and Maria Medina, who was also a postdoc, I think in Católica, and Davila and me. Okay, thank you very much for your attention.
Thank you very much, Manuel. A really nice talk, very deep results. So thank you for sharing with us this your recent discoveries. If there are any question, please, you can just take the just the mics are open, so please. I have a couple of points. I will start, Manuel.
Yes.
Um, so for the GP equation, this W and W bar, right, play the same role as the Kaufman-Scully profiles
In a way, you can say that. Yes, yes,
yeah. So
indeed.
but for the W, it was clear what equation they solve, right? You
Yes.
put it there, but in the Kaufman-Scully profile, you just mentioned the form of the function, but not where they come from, no?
You are absolutely right. You know, there is a technical thing why we chose that profile, okay? It has to do with the fact that 1 over 1 plus y squared is like the conformal factor you have to introduce to transform the Euclidean metric in R2 into the Euclidean metric in the sphere. This was something convenient in order to develop the linear theory that we needed. But in reality, if you consider things that decay fast, even compactly supported, okay, it goes well the same way, except that you have to work a little more. In fact, in our work with Parmeshwar, with the two vortex rings, the two vortex pairs, the two dipoles going in opposite directions. In that one, we needed, in fact, a compactly supported cores. So, in fact, you cannot find solutions that have that form if the basic cores are not compactly supported.
Yeah.
But let me say that essentially you expect that everything goes well for any radially symmetric profile that you put that has sufficiently fast decay, because all of them are steady stages, you see?
Okay. So the equations support many different kind of solutions.
Absolutely, absolutely. Essentially, you could even put different radially symmetric things, different weights, even different epsilons, you see, near each core. So there is a lot. Say, if you wish, GP is much more rigid than
Euler.
than Euler. Euler incompressible is too idealized in a way. Okay. What they say, in fact, the people for superfluids and so on, is that from what I have been reading, the GP is a more realistic equation, even though it looks more complicated and so on, and still quite ideal. But in reality, the fact that you have to take these circulations to be integers essentially is a natural thing for the problem. So somehow in Euler itself, it's not completely natural that you take them that way. Okay. But what you want to model still is fluids in certain regimes. So I mean, they are different equations. They are very much connected and they coincide in certain distributional limit, but they really have different difficulties. In fact, you know, one of the millennium problems, okay, is connected with this, which is the question if in 3 dimensions Euler and Navier-Stokes, okay, develop singularities in finite time. This is not known, and perhaps there's still a long way until that is proven or disproven.
Right. In the chat, Luis Japu asked the following question. He said, in quantum mechanics, the gradient of phase is already interpreted as a velocity in some way?
Yeah, honestly, I am not an expert, so I prefer not to invent an answer, but definitely this is the way they consider it. So the U is an order parameter, okay? The order parameter, what means is that it is measuring the superconductivity or superfluidity at each point. The absolute value of U, which is conserved, I mean the integral of U square is constant, okay? That's a conservation law. Imagine it is 1. Then the U square is interpreted as probability density for the property, say superconductivity, and the zeros of U are interpreted as places where the property of superconductivity or superfluidity or curves in 3D fail. fail to hold true because they are zero. Okay? And understanding these places where the property, the big property, superfluidity or superconductivity fail, is essentially the important matter, like the evolution of vortices or the evolution of curves in 3D. Yeah, I don't know if I am answering the question. Perhaps I don't have it much better. But the gradient of the phase definitely has to do with the degree of these zeros. Okay, the degree of these zeros when you consider U to be a map, a complex map from complex into complex. Huh?
Right. He said thank you. He said thank you, Luis. So, and another point was, very nice that this correction term related to the wave equation that defined,
Mhm.
right? So,
Mhm.
because the same thing that you were mentioning before, so for the Euler equation, it doesn't have sense
No,
to.
in Euler you don't see this thing because you have both in Euler and in GP, you have outer regimes, but they really obey to different things. The equation, the Euler problem, when you consider the outer problem, the regime far away, is still transport. Okay, that's the main thing. So it's still Hamiltonian if you wish. However, in GP it's not. You have these terms that they call radiation that are typically, they are solutions to wave equations. So they are sort of oscillatory behaviors far away. So they are small but oscillate. And in fact, something that let me tell you an example because this is a conjecture. Okay, if you consider two vortices with the same sign, they say if you consider them of different sign, they travel like this, okay, in one single direction. But if they have the same sign, they rotate one around each other, and they are periodic. Huh? On the other hand, in GP, because of this gradient term, what seems to be happening is that rather than generating a periodic true solution, if you try to find the true solution, the two guys get spiral out. They are getting far away slowly, but spiral out, and probably as time goes to infinity, you see still a rotation, but with very small speed, and so it's a completely different regime. That conjecture has not been proven. Huh? We are working on it, but it's not known yet. So really the radiation changes things.
Thank you, Manuel. Thank you. Well, if there are other further questions, so we thanks Manuel again for your very nice talk and nice results. So thank you for accepting our invitation.
Thank you very much, Eduardo. So it's an honor that you are introduction to. You are an important authority in Chile now.
Okay.
And
Well,
so at least for the next few days, right? Huh?
yeah. A couple of days, even a couple of weeks. Okay. So yeah, so to close our session, just to say to all of you that our next session is on June 17, and we will have